A very good morning all of you. Welcome back to HTLD lab. In today's lab session we are going to see how to design and simulate the synchronous counters. In the last lab session we have seen asynchronous counters. In the same way as your asynchronous counter, please refer to the lecture Synchronous Counters in HTLD theory course to understand the design perspectives of the synchronous counters. So in today's lab session we are going to simulate 2-bit, 3-bit, 4-bit up and down counters as well as up down counter. So let's start the simulation of your circuits. First let's start with the 2-bit up counter. Since it's a synchronous counter, as you can clearly see, the clock is given to the individual flip-flops separately. As usual, preset and clears are connected, common input for both the flip-flops. And in this case, your second flip-flop will toggle only whenever your first flip-flop output is 1. That means whenever this Q is 1 only, this flip-flop will toggle, else it will be in the same state. So let's run the simulation. So let's make it output as 0, 0. Then let's keep j equals to 1, k equals to 1. Let's start the animation or simulation. Now it is counting 0, then 1, 2, then 3 and again 0. This is a 2-bit up counter. Now we'll see the 3-bit up counter. Let's make the simulation to 1.5 Hz frequency. When you want to design a 3-bit up counter, the simple logic, if you want to understand a 3-bit up counter, your second flip-flop will toggle whenever first flip-flop output will be in the high state. Similarly, your third flip-flop will toggle whenever your first two flip-flops output is in the 1 state. So that is the logic for toggling the flip-flop outputs. Plus flip-flop will toggle for every clock pulse. Now we'll run the 3-bit up counter simulation. Let's clear the flip-flops, and j and k already kept it 1. The moment I make clear equals to 1, it is going to start the counting in the upward direction. Now you can see 2, 3, 4, 5, 6, 7 and 0 and so on. This is for the 3-bit up counter. If you want to increase to 4-bit up counter, you have to add one more flip-flop here, and this flip-flop will toggle whenever your first, second, third flip output is 1. Then only it will toggle. We'll see that circuit and simulation in a moment. As you can see here, the third flip-flop output, its third flip-flop input, if you look at here, this AND gate out inputs are coming from this AND gate. That means first flip-flop and second flip-flop as well as third flip-flop outputs. Whenever these three flip-flop output is 1, only this j and k becomes 1, then only this flip-flop will toggle, otherwise it will be in the same state. Let's clear the flip-flops. Let's start the counting process. Now it is going to count from 0 to F. So this is all about synchronous 4-bit up counter, or you can design it even in 5 to 5-bit, 6-bit depending on your user interest. Now we are going to see the down counter. When you design the down counter, only thing you have to do is you have to just connect this Q to Q bar here, and similarly for this AND gate you have to take this Q bar output and this Q bar output as input to this AND gate, and for this you have to take all the 3 flip-flops Q bar output as a input to this AND gate, so that this will toggle at appropriate state, so that we'll get a down counting that we'll see in a moment. Now you can see here this is a 2-bit down counter, which is a synchronous counter. Again, the clock is given separately to the 2 flip-flops. As you can see here, this flip-flop will toggle whenever your Q bar is 1. In previous case, like when you are doing up counting, whenever Q is 1, your second flip-flop used to toggle. Now whenever Q bar is 1, your second flip-flop will toggle. Rest all same, like your preset and clear inputs, everything is same. Let's run the simulation. Let's clear the flip-flops, and now let's enable the clock. Now you can see here it is down counting 3, 2, 1, 0 and 3. This is for the 2-bit down counter. We can increase to 3-bit by adding one more flip-flop here. By taking one AND gate here, this AND gate inputs will come from first flip-flop Q bar and second flip-flop Q bar, and clock will be given separately to the third flip-flop also. That we will see in a moment. So this is a 3-bit down counter. As I said, you can see here your Q bar output of both the flip-flop given to the AND gate, and this AND gate output is given to the JK input. That means the third flip-flop will toggle only whenever your first second flip-flop Q bar is 1, otherwise it will be in the same state. Let's clear the flip-flops and let's run the simulation. As you can see here, it is counting in the downwards direction. This is for 3-bit. You can extend it to 4-bit, adding one more flip-flop and adding one more AND gate. This AND gate will have input from this AND gate as well as this flip-flop Q bar output as a input to this AND gate. This AND gate output will be connected to the JK flip-flop to toggle whenever your first, second, third flip-flop Q bar is 1. You can see here, this is the extra circuit we added for the 4th bit. Let's run the simulation. Let's clear the flip-flops. Now let's make it clear equals to 1, so that you're going to count it in the downwards direction. C, then B, then A, then 9, and goes to 0. So this is how we can design 4-bit down counter using basic flip-flops. Now we are going to see the same circuit, like you are going to use only one circuit to do both up counting as well as down counting, that as we see in the asynchronous counter case. So we can reduce the circuit complexity by using up down counter in the same circuit. So this is a synchronous up down counter circuit. As you can see clearly, there are two AND gates now. These AND gates are controlled by a control input. This control input will decide whether Q should be act as an input to the next flip-flop or Q bar act as an input to the next flip-flop. If Q is act as input to the next flip-flop, then that will be up counting. When Q bar is act as input to the next flip-flop, that will be act as a down counting based on the control input. This control input will decide whether upper AND gate should be enabled or lower AND gate should be enabled, so that either Q will pass through to the next flip-flop or Q bar should pass to the next flip-flop. Let's run the simulation. Let's make it clear. Yeah, now it is running simulation. When control is 0, it is counting in the downwards direction, 3, 2, 1, 0. The moment if I keep my control equals to 1, it is going to count in the upward direction. Now you can see it is counting in the upward direction. This is for the 2-bit. If you want to go for a 3-bit, you have to add one more flip-flop. You have to add another 2 more AND gates up and. So we can easily extend it to 3-bit, 4-bit by extending the extra flip-flop, extra AND OR gate. The control input will be connected to those AND OR gates, like what we have connected here, which is similar to your asynchronous counters. So this is all for today's lab session. Thank you all.